And I think I need a little help here getting this going. Ooh, I got sound too. I wanted to start with this movie here around the world, and just here in Bellingham Bay too. We're experiencing more extreme flooding and also nuanced flooding more regularly. And a lot of folks are concerned about sea level rise. And to address these issues, I want to acknowledge some great people I work with, including Nathan, back here, a graduate student working on this problem. A number of partners all across the bottom there who help fund this work, developing a model for Puget Sound, and in particular Bert Rubosh, who was just instrumental in getting some of our initial model framework and real-time operational modeling going. But it's not just about sea level rise. It's really a lot about storms and waves that are going to be impacting our shores with sea level rise. This was just a couple years ago right here at Marine Park. Tremendous change occurred in just a very short amount of time. And we don't have yet a robust regional model of storms or waves throughout Puget Sound for planning. And it's also about sediment. So I want to talk to you today mostly about sea level and storms, but in the context of this diagram here called coastal squeeze. You heard a bit earlier from Bob Mitchell about how some of the high flows and low flows are going to be changing in the future. I'm just going to touch on that a bit, but focus most of the talk down here, how sea level rise, storms, and waves are going to be intersecting those flows and influencing a lot of what we really care about here. So I'm going to talk about some of the emergent concerns and mostly the impact pathways, not the impacts to us themselves. And this new coastal storm modeling system we're calling Cosmos, and some next steps. So I really like this picture because it just flattens out most of Bellingham to look very vulnerable to all the things I'm going to talk about. But really it's not. We're quite fortunate. There's a nice set of bluffs right behind the port. So we're actually not that bad off for some of the things I'm going to talk about. But there are key concerns down at the port, some of our transportation corridors, stormwater and wastewater treatment outfalls, and some really important parks. And then sort of other things that are out in the water that are very susceptible to storms, obviously. But probably more importantly is to think a little broader than just our city. You know, what really matters to us is our neighbors and our community at large and the regional economy of Washington that, we need. And a recent assessment suggests that the Lummi Nation and some of the outer portions of the county have much more vulnerability, especially to sort of the combined 1% river and coastal storm flood. We've seen impacts along some of their corridors for transportation that can be very impactful for several days at a time. And then throughout Washington, there's a lot of important resources here that we rely on. And an estimate is that by 2100, sea level may have up to $100 billion impact on Washington, coastal zones. What I want to focus a little bit more on here is sort of how we're thinking about informing habitats and coastal ecosystem restoration. And so this is a product that a number of us worked on here, led by CGS, an assessment of what we know about the condition of the nearshore and an attempt to prioritize what to do to restore a number of really important habitats. And one thing that came out of this was the need for a climate change assessment to then maybe prioritize some of these over others for resilience planning. And so we produced this right around the same time, which was an overlay of some of the storm surge sort of impacts, but just in a very static way, just raising sea level over this topography, but with a sense of what a 3-foot storm surge would be like. We have a scenario for 2050 and 2100. And again, it's really important to think that all of these possible actions for restoration are really within a context of what we need across Puget Sound, because a lot of our wildlife require habitats just outside of our neighborhood. And so this modeling system I'm talking about today really helps to bring a regional approach. So just a comment on this squeeze issue and the importance of future peak flows and sediment. We live below some of the youngest, steepest stratovolcanoes that have an enormous amount of sediment up there. And in fact, the Nooksack has sort of the largest sediment yield, so the largest amount of sediment coming per square area per time amongst all of our rivers. It's a fair amount of material. And with the freeze line rising, like Bob described earlier, it's liberating a lot of open space below the snowpack and glaciers for just rapid runoff. And it's the sediment part that's really critical. And we have a paper out last year describing what we think is going to happen in the Skagit River, and we think the Nooksack is going to be quite similar. But today's 100-year flood, given 20 climate change ensembles that Bob mentioned, run through his DHSVM model, but through our colleagues at SIG, suggests that today's 100-year flood by the 2040s is going to increase in magnitude by about 25% and recur as a 20-ish year event, so much more frequent. And it's during those really high flows when a lot of sediment can really move down through the system. We see 80 to 90% of the sediment moving down under big flows. And so we think there's going to be a lot more sediment coming down our systems, 3 to 6 times more given the mean flows, peak flows projected in the future, and just the range of flows. So just think of a lot more sediment trying to push through all of these river corridors. And so when it gets down into our coastal zone where we live and care about important industry and ag, we're starting to find evidence with new bathymetry and new analysis that in fact it's already starting to grade. Not so much in the Nooksack, but a meter, half a meter to a meter in most of the places we've looked. There's been lots of interesting changes in the delta itself, clogging up a number of distributaries, changing a lot of important aspects of it for, conveying flows through the system, raising flood risks, impacts to habitats and fisheries, access to fisheries, navigation. And we see this in many of the low rivers throughout Puget Sound, so it's not just here. Once it gets down into the coastal zone is really the question. It's always a fight between sediment influx and then waves and coastal processes that are moving that material around to build up the landscape that sort of leaves us either vulnerable or not. And so this is a picture based off of 1880s bathymetry, and as a lot of you know, I've been looking at sort of how this has changed. And so by 2011, this whole system prograded out about 1 kilometer. And so in some sense, this is going to protect us a little bit from some of the wave that I'm going to talk about. But at some point, that sea level rise is going to be impacting us more and more. This is the record up on the left of all of the main tide gauges from Seattle, San Francisco, and San Diego since the 1900 period. And you notice that there's these periods when the rate of sea level has changed. It was much more rapid in the middle of last century, tailed off a bit the last 20 or 30 years. And so we've been wondering when it switches back to a higher rate, we're going to be expecting some major changes. And that's what the bottom plot shows, is a recent paper of the last several years showing a marked increase in the rate of sea level rise along our west coast. And this has to do with large-scale sort of wind stress processes that dampen the sea level rise for a period of time that you see up on the right of the top plot. And now we think if this continues, we're going to see a much more rapid rate of sea level. We have projections for the future that are sort of ranging in 20 to 30 centimeters to upwards of a meter by 2100, and then just recently some other sort of projections with ice sheet collapse down in Antarctica that could actually send sea level up even higher. So think about what could up to a meter do to these projections. So this is what we kind of see every once in a while, just right here down on Rotor. This was just nothing having to do with the creek or the river flows. This was all coastal storm surge buoyed up and over the roads. And so what we're trying to do is build a model that adds a number of processes that are very predictable with sea level rise, sort of influences of El Nino and PDO that sort of oscillate through the system, and add what happens with extreme storm surge, waves, and the setup from waves, and their impact at shore. And we're doing this with a really interesting workflow with 20 different climate change ensembles run through a global climate model, predicting weather patterns, pressure and winds. We can also use the real-time winds, which I'll show you in a minute. We generate large-scale wave models, and then we scale those in nested finer models into places like Puget Sound, and it's been used in the California coast, right up onto shore where we use very sophisticated 1D models to calculate all the physics of waves shoaling on the shore and transforming, breaking, and what have you. And we want to do this now across all of Puget Sound at a scale of essentially every 100 meters. This is one of our outputs, and unfortunately it's not animating, but it was one of the storms in March of 2016, and I like to show this because on one of the two storms we had back to back, the low pressure was just so tight, and it was small on the spatial scales of, let's say, Bellingham Bay. And a couple days before that, on March 10th, we were able to do a really interesting experiment and measure the water levels in Bellingham Bay where we don't have any measurements being made continuously. And the water was, in fact, a foot higher in Bellingham than just 10 kilometers away at Cherry Point. And we think it's because it's kind of acting like a big catcher's mitt, and the waves are just sort of, wind and waves are raising the water levels, whereas at Cherry Point it's sort of flowing on by. This can have tremendous different impacts on our nearshore. The other question we get is just how are these extreme events today, and how are they going to change in the future, and how do we sort of put them into the context of change? And so every year we get these storm surge anomalies, and you can go to NOAA tide gauges where we have them and see the actual water levels versus predicted. And they can range a foot or to 3 above normal. Usually on average 14 per year above a foot anomaly. And they can last long enough, several days, where they intersect high stream flows and high king tides, which then have really important impacts when we care, when there's flooding and when a lot of agriculture is getting going in the system. What's really critical about this story, though, is when you look at the recurrence interval, this is shown in blue, and you read off what the 100-year sort of magnitude is today and how it would intersect a foot of sea level. You can read back over to see how that recurrence interval is going to change. And so today's 100-year event is predicted to change to become much more of a 2 or less than 5-year event here in Puget Sound. And it's looking like this on a number of stations across the West Coast. It's really interesting. So here's an example of one of our models. It's for Bellingham Bay. We've got the tides and the sort of total water level predicted on the bottom, going 48 hours out. These are real-time operational forecasts. Winds on the left, and this is for the next couple days. Waves on the right. We're not going to see a whole lot because the winds are going to, I think, change to the north and northwest, so we can go check that tomorrow. There's some validation. And then we are validating this with water levels, wave measurements, and then we have a citizen science project, a storm surge monitoring program across many of our northern counties. A number of you are here with us today that help us examine the impacts at shore when those occur. And if anyone's interested, just let me know. So a couple quick applications of sort of how we're using this for habitats and ecosystem planning, and then I'm going to end with sort of what we want to do in the basin here. We have this ongoing project with the Swinomish tribe and a number of other partners to look at how beaches for shellfish and forage fish are changing and likely to change with greater amounts of energy that winnow those fine sediments out of the beach and leave coarser material. Some of the clams that Swinomish care about really depend on a certain fraction of muds and sands. We're also looking at how these barriers, the spits and barriers that surround pocket lagoons and other beaches are going to likely to be migrating, so we can sort of look at the cumulative shear stress over time relative to the critical bed shear stress of the material on the beaches. And we're also looking at shellfish larval dispersal and sediment. Now you'd think, most of our storms are coming in winter, where we have a few recent episodes of major storms in summer and sometimes in spring, and those are likely going to change in the future as well. Another real important use of this is estuaries. Some of you may know that we're working on the Nisqually River Delta sort of restoration. And because of a sediment deficiency, largely because most of the load bypasses the delta and gets offshore initially, there's about 100 to 200 year time frame, given the sediment load today, to recover those marshes and the subsidence that those marshes have sustained. And so we've evaluated a number of restoration alternatives to see if we can reroute sediment, and it's looking like they can't really do enough just through typical channel distributary connections. However, the waves may play a really important role in stirring sediment offshore and actually during storms bringing sediment up. And so this wave modeling is helping us to do it. So I think I've got just 2 slides left. And this is an example of into the Skagit River, much like the Nooksack, how these tides and storms affect the current velocities that move sediment out of the system. And it's a little tricky to see, but this plot down here shows that during a very sort of high water event, 3 feet higher than typical predicted, we actually depress current velocities in the lower portion of the river enough that it promotes the sedimentation that we're seeing these days. So it's a very useful tool to see then how things are going to change in the near future. So our next steps, and I wanted to show you output of our new unstructured flow model here for the Nooksack, but we have this now coupling with the waves to then look at a number of these issues and interactive processes coming through the estuary. And what we really want to do is evaluate, so how are these higher waters, more frequent high stream flows, and longer duration coastal waters going to be influencing the wave propagation in the sort of what I just described as the sort of backwatering of the river, extra sedimentation up in the system, as it will then affect flood risk, groundwater ponding and drainage issues that are being noted, shoreline and habitat impacts, including sort of what's happening to shellfish beds along the beaches here. And then there's a number of infrastructure problems that other cities are dealing with just like us. Typically, longer duration high water backing up stormwater outfalls right on up to the treatment plant and causing corrosion and what have you. And then there's also a really interesting aspect of mixing the whole water column, mixing the acidity that David just talked about, mixing up the bottom sediments that often have different algal cysts that can be dormant for up to 70 years and actually, when they get resuspended, produce HABs. And this is a whole new train of work that DNR and DFW are interested. I think a number of tribes are as well. And so these are just some of the things we want to bring. It's a bit of expense to sort of build this model for Puget Sound. We're getting there in fits and starts, and it'd be fun to work with anyone here to do that. So thank you so much.
Hi, so FEMA's has proposed remapping of our 1% annual chance along Bellingham and Whatcom County's coastline, and I was just curious to see if you've been involved in that and make sure that your work has been shared with them. So.
Yeah, absolutely. They're a regulatory authority with a very different mission with the coastal firm mapping. The basic bottom line differences in what we're doing is that they're only modeling sort of the historical calculated 100-year coastal and river flood events. They're not necessarily projecting into the future with sea level rise or any of the climate change patterns that I've been talking about. They have, we've been working together just recently as they came out with some of their products for Skagit and Whatcom County. They're actually very interested in using our model outputs that are predicting the physics during a storm approaching and all of the physics at once that reach the shoreline, and using our outputs to test whether their 100-year mapping is correct or not. And so we think the last couple big storms we've had, 2016 and 2006, are fairly representative of some of the most extreme storms we've had, at least from sort of the south direction. There's a few others on the Sandy Point shore that are different, but those are, yeah, that's in the works.
You talked about that in sometime in the future, the 100-year return will be 2 to 5 years. Can you say what decade your models are showing that?
You know, that's going to be a critical sort of answer in just about a month. We have another project going. It's a Washington State Coastal Resilience Project where we're developing a probabilistic sea level rise model for the entire Puget Sound, and it includes vertical land motions and the best knowledge of sea level. And with that, we will have a better number and an error around that date that you're looking for.
Okay.
Currently, we're seeing about 2 millimeters per year of total sea level rise at places like Seattle, a little less here, we think. And so you can kind of do the math to figure out sort of what that would be. But the distribution of these extreme water levels is just so narrow. It's essentially 30 centimeters to 40 centimeters between a 100-year event that we've seen in our past and a 5- and 10-year event that we're seeing in our past. So it's just really stark, and a little bit of sea level rise just shifts that whole distribution over. It's interesting,
Thank you.
to say the least.
Yeah,
Thank you.
George.